Hello, my name is Bartek McCormick, and this is the Random Number Generator project. And I worked on this project with Devlin Moody, and I'm going to be going through a presentation going over how the random number generator circuit works and how you're able to take the function of a die and convert it into a circuit. So the circuit itself consists of multiple sections, and the first of these sections is the analog section, as you can see right here. This is a picture of it on a soldered circuit board, and here's the same section in multisim. So the components that this consists of is the 555 timer, multiple capacitors, and multiple resistors. So you can see right here you got one of the capacitors and two more of the capacitors. You got your three resistors right here, and you have your 555 timer right here. So the purpose of this is to create the analog signal originally, which is then converted through the 555 timer into the digital signal, which is going to be used elsewhere in other parts of the circuit. And this also creates a dice roll effect with the LEDs, which I'll explain at the end of the presentation. So the explanation for how this works and how this creates the first part of the circuit is when you push down a button on the circuit board, this is the part that you're working with, and when you push it down, you're closing the gate. You're providing this capacitor with a constant stream of voltage. So you can see how it's charging and discharging, charging and discharging at a constant rate, constant frequency, constant period. And you can see right below it is how this is the output, which is a digital signal. This is kind of the input, what goes into the 555 timer. So you can look at these two simultaneously, and when you let go of the button, which is when this gate is open, that happens right around here. There isn't a constant stream of voltage coming to this capacitor. Some of it's being grounded, some of it's going elsewhere in the circuit, and it takes longer for this capacitor to become charged. So as you can see, the period is increasing, the frequency is decreasing all the way until it stops. So this is essentially the basic principle of how the board works, and I'll explain how it interacts with the other pieces at the end, or the other sections. So this digital output, it goes into the sequential logic section of the circuit, which is right here on the soldered board. You can see it's these three flip-flops, and basically you can see them right here as well. So as I said, these consist of three flip-flops, which creates a 3-bit counter. And so the whole purpose of this is to create that 3-bit counter, which allows for the circuit to count from 1 to 6, and it allows for a random number to be picked from those 6 digits. So this is how it works. It's a binary version of 1 through 6. So how that works is you have your this represents the 555 timer, which is essentially a clock, and for the purposes of this, it's a constant high to low signal. So if each cycle you're gonna have your digit from the binary, the binary digit is gonna increase. So what happens is the first cycle will be 0, 0, 1, which corresponds to 1. Then it'll be 0, 1, 0, which corresponds to 2. Then it'll be 0, 1, 1, which corresponds to 3, etc. So that is basically taking your digital signal and turning it into a binary number, which is going to cycle 1 through 6 repeatedly, with every cycle. Um, so then that leads you to your final section of the circuit, which is the combinational logic section. And this is a picture of it on the soldered circuit board. As you can see, you have your, well, I'll go into what it consists of in a second. Here is what I'm circling right now is, or what I'm circling right now is what is the combinational logic section, and this is a picture from multisim. So it consists of OR gates, AND gates, inverters, resistors, and LEDs. And yeah, so the purpose of this is to take all the possible outputs from the truth table, which is essentially the binary outputs of the sequential logic section, and it provides LED outputs that correspond with the binary number in order to create a more usable interface, and it makes it a lot more accessible. So how that works is this part right here, it essentially represents the output from the sequential logic section. So this basically represents a binary digit, and you're gonna have it go into this combinational logic, and it will create an output with the LEDs that correspond with the face of a die. And so how that works would be, for example, for 001 in binary, which is 1, it would go through this combinational logic, and the output would be that LED 4, which is right in the center, would light up, and that corresponds with 1. So before I explain the whole system and how it works together, I'm going to show a little video of the soldered circuit board itself working. There you go. All right. So as you can see, once it's powered and you push the button, it will cycle through the numbers, and it will slow down and land on a single number. So how that works is, it's easiest to explain in multisim, so that's what I'm gonna do. The first part is the analog part, as I explained, and what it does is it creates an analog signal. It converts that signal into a digital signal, and so you're gonna have your gate, and when you push down the button, as you could see in the video, when you push down on that button, you're gonna be closing the gate, and the capacitor is gonna be able to charge and discharge at a constant rate, since it's being powered by a constant stream of voltage. So once you let go of that button, however, the gate will open, and there won't be a constant stream of voltage available to the capacitor. Some will be grounded, some will go elsewhere, and basically end up back in that capacitor, and it will take longer to charge, and it'll take longer to discharge until it flattens out. And so that basically corresponds with, as I was talking about earlier, the dice roll illusion that is created by the LEDs, which is how at first when you hold down the button, when you push it down at first, it's cycling very fast, and then it slows down until it lands on a number. That's because the capacitor is it takes longer for it to charge up and longer for it to discharge until the point where it stops. So it creates this gradual stop. So that output from the from the analog section, it goes into this section right here, which is the sequential logic section, which, as I said, it's a 3-digit timer, which is made from 3 flip-flops. So with every cycle that is being inputted, it's cycling through 1 through 6 in binary very fast. It's going 1, 2, 3, 4, 5, 6 very fast. And as the frequency provided by the analog section is decreasing, it's going slower and slower and slower until it stops on a number. So that creates the illusion that this is a random number generator. It's not exactly a random number generator since it's based on time, but for human application it's sufficient due to the fact that it's a very small interval of time, so it appears to be random. So with that binary output, which corresponds to a number, that's not very intuitive if you just have that output. So it goes into the combination logic section, which uses multiple gates, the OR gates, the AND gates, and the inverter to take that output and to put it into something a lot more accessible, which is the face of a die, which is simulated with LEDs, LED lights. So as you can see on this picture, you have the binary number 0, 1, 1, which corresponds with 3. So that number, that output is the input for the combination logic section. It goes through all of this, and there you have the output, which is LED 8, LED 11, LED 14 in this picture. They light up, and that's the output of 3 on a regular die, which is a lot more intuitive than 0, 1, 1. So that's the end of the PowerPoint. That's the end of the presentation. Thank you for watching.